Welcome to Wireless Future. We are back with another episode, and I'm Emil Björnsson as usual, and I'm here with Eric Larsson. How are you today?
Hi Emil, I'm good. How are you?
I'm fine. It's sunny weather outside, and it's even started to be hot sitting here just talking to you.
It is indeed. I mean, it feels good to be back in the studio where it's cool and comfortable.
So we have had a number of episodes lately. I think this is episode number 14, and it's been a while since we had a Q&A episode, and we have covered a number of topics since then, like cell-free or distributed MIMO and terabit per second, how we can achieve that, and non-orthogonal multiple access or NOMA. So for this episode, I have been going over the internet and gathering some of the questions that we have received in different ways, and I was planning to let us answer 10 of those questions. Does that sound all right to you?
That sounds like a plan. Episode 14. Wow, that's amazing. So,
yeah.
Well, let's go ahead.
So the first theme, I've categorized this into different themes. So first we will talk about MIMO communications or cell-free MIMO and distributed MIMO. So the first question goes to you. Does channel hardening hold for channels with correlated fading?
So channel hardening and correlated fading. I think we need to recap what channel hardening means, right? So channel hardening means that the effective channel that the terminal sees, let's talk about single antenna terminals here. So the terminal will see then a scalar channel, right? An effective scalar channel. And hardening means that this effective scalar channel fluctuates only a little around its statistical mean or its statistical expectation. And in massive MIMO, this happens because on downlink, when the base station is beamforming, essentially what the terminal receives is a superposition of contributions that comes from all the base station antennas. And then by large numbers, these contributions kind of, are the sum of these contributions is close to their statistical average. So the question is, when does this happen in terms of different fading models, right? And with independent Rayleigh fading, this happens because the effective gain will then be, the optimal beamformer will be the conjugate of the channel. So the contribution to the effective gain from each one of the base station antennas will be the channel gain square from that antenna. And then we sum up these squared gains over many antennas. And that sum is, if the gains are independent, then the sum is approximately equal to a constant, which is the statistical mean. So that's what happens in independent Rayleigh fading. Now, in correlated fading, I think we first have to distinguish between, what type of fading do we have, right? We could have, for example, Rayleigh fading, where there's a strong line of sight component, and then the gains themselves are nearly deterministic. So yes, there would be hardening, irrespective of, whether you have correlation or not. But very often, I think in the literature, correlated fading refers to correlated Rayleigh fading, in which case we have the Rayleigh model, but where the gains aren't independent. So there is correlation among them. And what we have in terms of the effective gain, this effective scalar gain that the terminal sees, will be a sum of many squared channel gains, but these are correlated, and then law of large numbers kind of doesn't hold the same way any longer, right? We sum a number of random variables, but they are correlated, so that sum fluctuates more around its statistical mean. And with correlated Rayleigh fading, then the the lower is the rank of the channel correlation matrix, the more heavily correlated are these gains, and the more the effective gain will fluctuate around its statistical mean, so the less hardening. So the lower is the rank, the less hardening. And in terms of physical propagation, a lower rank means a smaller angular spreads. So the signals coming in or the say for the uplink, then the signals coming in from a smaller angular window. That would be lower rank. I'm sure you want to fill in something here, Emil. You worked extensively on correlated Rayleigh models in your research work.
Yeah, no, I think that one way of motivating geometrically that one would get it kind of independent or uncorrelated Rayleigh fading is that signals are coming in from all directions to the base stations uniformly distributed, and if they are not distributed over all angles but confined to one angular window or a few different ones, then there is less variability, and you need a lot of variability for this averaging effect to appear. So every single element still sees the same fading as before, but when you put them all together, the fading averages out.
Yeah, I mean, this is a rather technical question, which is kind of difficult to answer without going into actual mathematics of these fading models, right? Which is done in various papers, and I think in your recent book on massive MIMO networks, you also have a fairly thorough treatment of this correlated Rayleigh model and its effect on hardening. So it's hard to give, like, without visual aids, a more precise or substantive answer than what I just said, I think.
Yeah, but I think I have an example in that book saying that suppose that with uncorrelated fading, if you have 50 antennas, that is enough to see a lot of channel hardening. And if you then have a lot of correlated fading, strongly correlated fading, you might need 200 antennas before you see the same type of hardening effect. So it's sort of those things that can happen. Can we create channel models where you can just go on adding antennas and you never see any channel hardening?
Oh, that's a good question. I don't know. I'm sure you can. I mean, the question is whether such channel models have much of physical meaning.
Haven't you studied something called the keyhole channel?
Yeah. Keyhole channel is, to my understanding, mostly a theoretical construct. I mean, it is something you probably could build and measure in the lab, but you really have to build it. I mean, the idea is that you have like an array that could potentially be large behind a large conducting sheet. Think of like a metal sheet, and then in that metal sheet you cut a small slice so that any wavefront that like escapes from this little cage with the antennas and then covered by the sheet here have to escape through that little slice or that little slot. And the question is, I mean, how often do you see that sort of phenomenon in practice, right? But if you do, then sure, because every wave that emanates from this like cage would creep through that slot, you'd effectively have a single antenna system. So that's right. I mean, with keyhole propagation, there is no hardening. That's correct. So it's not hard to cook up models under which hardening breaks down, right? But then the question is how common, or I mean, can you even find examples of practical situations where you see that sort of propagation? But that said, I mean, hardening is an important phenomenon that can be exploited for various purposes in massive MIMO transmission. One effect of it is that because the effective scalar gain per terminal hardens and is essentially equal to its statistical expectation, that means that every subcarrier, say in an OFDM system, becomes equally good, right? So there's no point in scheduling over the frequency domain, the same over the time domain for that matter. And also, for the same reason, the hardening simplifies a lot of tasks that used to be quite complicated. Power control, for example, which now becomes independent of subcarrier index and independent of the time slot index. So it is an important thing to understand when working with, not only with the physical layer massive MIMO models, but also when understanding and developing MAC layer protocols and higher layer system functions. All right, great. So maybe enough about hardening. Yeah. Okay. So the second question here is, how does cell-free massive MIMO perform compared to conventional massive MIMO? Can it provide an order of magnitude higher spectral efficiency? Is cell-free massive MIMO really a game changer? Do you want to have a go at that question, Emil?
Yes. So when we talk about spectral efficiency, there is different ways of measuring spectral efficiency. So we will have a collection of users. So we can talk about the maximum spectral efficiency, that you can ever get somewhere in the network, or you can have the average one as you move around the network, or you can have something that you can guarantee. I think it's often called the user experienced or 95% likely spectral efficiency, what you are getting 95% of the time as you're moving around in the coverage area. And the purpose with cell-free massive MIMO, so sort of distributing antennas over the coverage area and let them all serve you, is not to push up the peak, the largest value, or I don't think it even is the goal to push up the average, even if that might be the side effect, but really try to even out the variations and making sure that you are getting a good spectral efficiency or reasonably lower level of spectral efficiency everywhere. So I think the problem of the networks of today is not that the peaks are too small, but it's rather that the valleys in performance are bad. I think I seldom need more than maybe 5 megabits per second to stream something, and the networks can deliver much more than that, but when you have bad coverage you don't get that. So I would say that the goal with cell-free massive MIMO is to push up this user experience rate, and there is definitely a good opportunity for game-changing improvement. So in my book that we were mentioning last time, I was running some simulations where we were trying to compare massive MIMO and cell-free massive MIMO. And it's always hard to compare different architectures, but we were saying, okay, let's say every base station have 100 antennas. If it's massive MIMO, and then we take the same number of antennas and spread them out over the coverage area, one antenna per access point. And then what we saw was that for the 95% likely rate, so what you're getting most of the time, you can get a 5 times higher rate. So that is not an order of magnitude, which typically means 10 times. But if you also would put up more antennas, if this is a way of putting up more antennas or play around with other things, you could probably push it up to an order of magnitude. But even if you don't reach that, I think it still can be a game changer in terms of what you as a user are experiencing as uniformity in the service quality.
Yeah, of course the question is, I mean, what does order of magnitude mean, right? But base 10, it would mean like 10 times. And then the question is, so, and this is ultimately, I think, a business question. I mean, what is worth more, right? That we boost the peak rate from 10 megabit to 100 megabit, or that we boost the coverage from 90% to 99%, or 99% to 99.9%. And I guess bottom line here is really that one of the main selling points of the cell-free architecture is that by virtue of all the macro diversity that it offers, it is this uniformity of the quality of service and essentially the elimination of coverage holes, which means increase in coverage or increase in reliability from like 99 to 99.9. That's really the core of it, right? The main selling point here.
Yeah, and it's really this feature of distributed MIMO that the antennas are cooperating that is providing us with this improvement. Because in the same simulation we were saying, or looking at the case where you have this 100 antennas spread out, but you let every antenna form its own small cell, and then they were interfering with each other. And that one was giving us essentially the same performance as massive MIMO as you're moving around. So it was sort of... maybe we should view cellular massive MIMO as the convenience of not having to put up a lot of small cells, but instead have one big base station. While if you're putting up those small cells to actually make them useful and get good improvements, you need this distributed MIMO feature on top of it.
Yeah, that is exactly the point. I mean, small cell solutions, they simply do not work, right, in terms of providing this uniformity of coverage, which is, I mean, where it all started more or less with cell-free massive MIMO. And it's reassuring to know that you guys have now also new simulations that further amplify on this point, because it's such an important message, I think, to the community to realize and to understand the distinction between small cell and ultra dense and all this on one hand, and fully coherent cell-free massive MIMO on the other hand.
Yeah, and I've heard this also from people who are trying to deploy small cells in reality, that interference is a big issue.
Yeah.
So I have a question to you. What are the main challenges for scalability and power control in cell-free massive MIMO to enhance spectral efficiency and energy efficiency?
So the main challenges in terms of scalability and power control. So, I mean, the issue here is that when we scale up the size, right? I mean, add more and more access points that are all connected to the same central processing unit. At some point, we're going to create, well, there'll be immense problems with just getting the data processed and collecting the data to the central processing unit and all that. But I think the question here pertained to power control. And, well, so in principle, there are algorithms out there that can optimize the power control coefficients in a cell-free massive MIMO system to achieve a certain objective, which could be to maximize the sum spectral efficiency or to optimize for max-min fairness and so forth. And these algorithms are, number one, quite demanding computationally, right? I mean, they require like solving very complicated optimization problems that has to be done at like at the central processing unit, more or less. And also they require the central processing unit to have access to all pertinent information, which means like all path losses and pilot assignments and all that, right? Which it, for that matter, might have. But anyways, it's a complicated problem to solve, and this computational complexity grows. Might be polynomial, but it grows very fast, right? So at some point, it's just not feasible to do this any longer. And then the question is, what do you do? So one thing you can do is to say, okay, so we got this area that we want to cover with a single central processing unit and a single power control policy, but it's not feasible for computational reasons to do it. So we'll split this and say that, well, in the left part of the area we run power control independently, and then on the right part of the network we run power control independently. And then what happens is that these two parts won't easily directly be able to coordinate with one another, so that what is good for the left part of the network might be bad for the right part of the network, in particular for users that are located like almost in between or at the boundary between these two parts. The question is, which part is it really that's going to serve this user? And when we solve the power control policy problem for the left part of the network, then how do we consider this user as compared to when we solve the power control problem in the right part of the network? And also making a small change in the power control policy of the left part of the network might impact the interference situation in the right part. And then the question is, now if we have a really large network, so we have not only a left and a right part, but we have 100 different parts, then will this eventually create some sort of butterfly effect where you make a small change in the power control here and that will affect what goes on in the neighboring part of the network, which in turn affects what goes on in the next neighboring part and so on. And it's like, you can't solve an optimization problem, which is fundamentally combinatorial, right, to its global optimum by breaking it up into small subparts and solving the subparts independently. It's mathematically impossible. So for that reason, to build power control policies that really scale, one has to apply heuristics. And fortunately, it appears that relatively simple heuristics are pretty good here. Not optimal, but pretty good. So I don't know whether that answers the question.
Yeah, no, I think that is a good answer to the question. And let's see if you agree with this statement. I think the downlink power control or allocation is the more challenging part, because in the uplink, you could always deal with some of the things in the processing later on. Even if people are interfering a bit too much with each other, you can process it to deal with that. But in the downlink, sort of the interference is created over there, so you need to control it in the beginning.
That's certainly true. And in addition to that, I think it's also true that on the downlink, there are a lot more variables to optimize, right? Because on uplink, if you have 100 terminals, then you have 100 power control coefficients, and that's it. But on downlink, if you have 100 terminals and, 100 terminals and, say, 1,000 access points, then each one of the access points will have to have a power control coefficient for each one of the terminals. So in aggregate, we'll have 1,000 times 100. That's 100,000 coefficients to optimize. It's like a more challenging problem from the computational perspective as well. So downlink is really the hard part here. All right, great. Maybe next question. What frequency band is cell-free massive MIMO meant for? What do you think the first use cases will be? Do you want to have a go at that question, Emil?
Yes. So I think that the concept as such is something that we can apply in any frequency band, but I think that the characteristics and goals of it might be different in different cases. So in the conventional lower bands, 1, 3, 6 gigahertz, then we will have the situation with rather good propagation conditions. So if you put up many access points, you will be reached by signals that are non-negligible for many of them, and that is when they need to cooperate to transmit to you and deal with interference. And I think this is the sort of the good band in order to provide this kind of uniformity of quality of service. Then if we are going up in frequency and we are using like millimeter wave bands, then one of the issues that we will see, particularly when we go up even further, is the blockage issues. So where the signals can be blocked by your hand or by different objects, and in those cases you can put up many access points around you, and you might not benefit that much from them cooperating in order to transmit jointly to you, because maybe you only will have a strong signal for one or two at a time, but and there might not be so many users in the area because the coverage of everyone is small. But you will need this kind of macro diversity, the fact that there is always if you block one signal, there will always be another direction that the signal can come from. In terms of use cases, I would say that the first use cases might be the cases where we already see deployments of like indoor cellular technology. And these are places like airports, shopping malls, hotels, and maybe some entertainment locations, some stadiums. I think in particular it should be cases where there's a lot of people and the people are in motion. Maybe a stadium where people are sitting still, you can put Wi-Fi above them and it will be fine. But in many other situations where you need to deal with interference, a lot of users, people moving around, then cellular technology is used now to create small cells, and that is where, when the usage is increasing, you will need this additional feature to deal with interference. And then maybe also cultural places where we are not allowed to put up conventional base stations, even if they would be a good option. They are too ugly to put up. So then this kind of new technology that is almost invisible because it contains many small antennas could be useful.
So basically you're saying, I mean, there might be the two driving forces here. One is as we touched upon earlier, right, with the uniformity of the quality of service and coverage and all that. The other is potentially also an aesthetical reason that you don't want like conventional panels on top of like an old church or something, but rather if you were to install any wireless infrastructure there, it would be in the form of small antennas that are just integrated naturally or embedded into like the structures of the building and therefore not visible to the bare eye.
Yeah, no. Around where I live, you can also already see people who try to hide base station by just painting them in the same color as the roof. I've seen there's a black antenna, there's a red antenna, and this is sort of the next step where you actually are hiding it in the building elements of the building already.
Right. Yes, this is neat. Yeah. Okay.
Okay. So let's now switch theme and talk about like terabit per second or terahertz communications. And I have a question for you. Can visible light communication be useful to reach 1 terabit per second? And I mean, there is 400 terahertz of spectrum in that range. That should be useful.
Oh, yeah. Okay. So I'm not sure if I'm really the right person to answer this question. I mean, visible light communications is an emerging technology where I'm not quite sure what the ultimate limits really are there. I mean, obviously, if you could communicate coherently over such a huge chunk of spectrum, you could probably, reach these numbers that the question mentioned here. But to my knowledge, current technology for even over short distances using like LED transmitters reaches at most a few hundred megabits, perhaps half a gigabit, or I don't think much beyond that. I mean, so there seems to be like a couple of orders of magnitude here. And if you just think of like, if you could communicate coherently right over this bandwidth, yeah, sure, but the technology is not even close there. So answer is probably no in the in the near term, at least as far as I have understood.
Yeah, no, we have so much bandwidth in those ranges, but anyway, we are not beating conventional 5G technology. So for it to all of a sudden beat it and move much beyond this, it might not be that is the goal of visible light communications.
Yeah. No, I'd probably agree there. Well, continuing on this line of very high frequencies, but not that high, fully as high, okay? This is the next question here on whether massive MIMO has a role to play in terahertz communications. And I suppose terahertz here means now, well, from where's the definition of terahertz? Is that from 300 gigahertz or something and up, or how's that really defined? To start with?
That is interesting because in a way, millimeter wave communications would go all the way up to the wavelength of 1 millimeter, which is 300 gigahertz, and I get the impression that since millimeter wave nowadays have meant up to say 100 gigahertz, then everything above that people start to call sub-terahertz or even terahertz communications. I will focus my answer to maybe on that range between 100 up to 300 or 1 terahertz or something like that. And yeah, one of the issues that you will see in those bands is that the propagation condition gets worse because of the signals are not interacting as well with objects anymore. So it's sort of continuation of the issues in the millimeter wave bands, and also for a fixed gain antenna, the size of it will shrink, so it will sort of collect less and less energy. So when it comes to massive MIMO, we have these two main interesting gains of it. The one is the beamforming gain, where you have a collection of antennas, so you focus energy, and that will be very useful in order to overcome some of those path loss issues that you are losing more energy along the way, or just to build up the same aperture at the receiver, so you're collecting the same amount of energy. And then also, if the whole point with terahertz communication is to use, say, 10 or maybe 100 times more bandwidth, then to get the same SNR, same signal-to-noise ratio, you would have to have 10 to 100 times more transmit power, which typically it's rather the opposite effect, that the higher you go up in frequency, the harder it is to create power amplifiers that can provide us with such strong signal power. So then you could compensate with having more antennas, so you're focusing the signal energy even more. Then there is another interesting thing, that second gain, multiplexing gains, that we have with MIMO, where you transmit multiple streams. And what we are usually referring to in massive MIMO is the fact that you could serve multiple users located in different directions. And one of the reasons to focus on that is that in lower frequency bands, the device will be so small that you might not fit so many antennas into it, and even if you fit many antennas, each of them will observe roughly the same signals, so you can't really send different beams to different parts of the receiver because you don't have a good rank of the channel. But there is something called the Fraunhofer distance, as giving a rule of thumb on at what distances you can actually observe that the waveforms are like spheres and not looking almost flat. And when they are spheres, you can send different spheres to different parts of the surface of the antenna, and therefore you can multiplex multiple signals. And I was just making a simple computation. Say that your receiver is 1 decimeter times 1 decimeter, and then at 3 gigahertz, this Fraunhofer distance is 2 decimeters. So if you are above 2 decimeters, you can only send 1 stream. If you go up to 30 gigahertz, you then get 2 meters. And if you go up to 300 gigahertz, you have 20 meters. And probably the range of the systems will be much less than 20 meters. So in those cases, you can actually send multiple streams to the same device in line of sight, even if there's no other objects that are providing you with extra paths. Just by seeing that you have different shapes of the wavefront, you are able to send multiple streams.
So, I mean, basically what you're saying is the aperture has to be large enough compared to the transmitter-receiver separation, right, in order for the channel to have enough rank so that you can support the transmission of multiple parallel streams. Then, of course, in a multi-user system, you could have like the users spread out, right, and in different directions, and then you could multiplex to many of them at the same time. But interesting.
Okay.
Great. Okay, so next question here is on power consumption, and specifically the power consumption of AD converters, which has been a major concern for millimeter wave communications, even at, say, relatively low bandwidths like a single gigahertz, right? And I think when we talked about terahertz a few weeks ago, then we mentioned the possibility of using really huge chunks of spectrum, like 50 or 100 gigahertz, to reach this terabit per second goal, right? So what do we have to say about power consumption if we were to build anything like that? Do you want to have a go at that question?
I remember 5 years ago or more than that, and when people are talking about millimeter wave communication and using multiple antennas in those cases, one of the big showstoppers were supposed to be the analog digital converters. And I think the reason for that is that we are used to having like 15 bits per sample when we're sampling things, and then the power consumption is of an ADC. This is complicated to talk about how things are scaling when you're changing technologies, but as a rule of thumb, the thing is that the power consumption will grow at least linearly with the with the frequency that you are or the bandwidth, so the sampling rate. And then if we are going up by 100 times in bandwidth, we will have 100 times higher power consumption. And that will then be a major issue. But then what we can compensate with is the fact that while it grows linearly with the sampling rate, it grows exponentially with the bit resolution. So if we are instead going down in bit resolution, so instead of having 15 bits per sample, we might have 6 or 7 or 8 bits. We can reduce the power consumption a lot in that way. And I think this is one of the things that are being considered when it comes to millimeter wave communications already. And this was already mentioned in the podcast that we had a guest talking about how you can build fully digital millimeter wave solutions. And I was looking around in the literature to try to find some kind of ADC that could be utilized for terahertz communications. And I found one that is from 2018 in the paper, 128 gigasampler per second. So you take 128 billion samples per second, and it's meant for having like 60 gigahertz of the bandwidth. And every sample is around 8 bits. I think the way to achieve such high sampling rates is essentially that you have multiple small sampling devices that you're timing the leaving, so you're switching between them. That way you're pushing the limits. But the circuit was consuming like 320 milliwatts. So that is not a big number. Then if you will build an array with many of them, then it will of course grow up and becomes many watt of power. But just one device shouldn't be a problem. I think the reason that there is already development of this kind is that this is needed for fiber optical cables where we push the limits.
Yeah, I mean, as you said, I mean, 300 milliwatt is not really a lot, right? Well, it might be a lot if you're powered by a small battery or something, but it's not really a lot if you, in terms of, I mean, problems of to cooling, for example. If you have a single amplifier, if you have thousands of them, then it's an issue, right? So you could build something like a millimeter wave transceiver with an integrated frying pan, or I don't know. But so basically, the key take home here is that the power consumption goes linearly with the bandwidth, and that's not such a bad thing. But what's really bad is that it goes exponentially with the resolution in terms of number of bits, and therefore there is great value in being able to cut back on that resolution and quantize the signal more coarsely, which we know is entirely feasible with MIMO transceivers, give or take. I mean, there will be issues with potential issues with out-of-band blockers, for example, that will have to be dealt with, right? But in principle, with enough, say, randomness in the propagation environment, then quantization noise will average out to a great extent, which facilitates a reduction in the number of bits, which in turn gives a great payoff in terms of the energy consumption in these ADCs.
Yeah, no, and I think what we also talked about in that terabit per second episode is that we are not targeting to have that high modulation formats for every symbol that we're transmitting. So if we are, say, targeting 16 QAM modulation, so we send 4 bits of information per sample, then if you take 8-bit samples, that should be enough to actually decode it rather well. That's also a reason that for the signal itself, we don't need high resolution, but as you mentioned, we might need it to deal with other types of distortion effects. So we might have to give up a bit on the robustness of the system, or if you have multiple antennas, you can take it away by being able to sort of spatially remove some of the interference. But I think the question is touching upon a very important thing, namely energy consumption. So whatever way you're building the system, there will be a cost in like joule per bit that you want to transmit. So for a given type of architecture, if you are increasing the data rate by 100 times, the power or energy consumption will grow by 100 times. So for like handheld devices, it might be very far-fetched that they will be utilizing a technology that is able to continuously transmit at these huge data rates. So either you have it for the possibility of just transmitting a lot of data over a short period of time, and then you are not using it continuously, or you use this for kind of fixed links where you are not concerned with power consumption in the same way.
Yeah, it's a good point. I mean, I think for handheld, it's also difficult to envision what sort of applications would require this sort of data rates continuously, right? You could imagine that you'd need over the course of like a fraction of a second to send an intense burst with data at an extremely high rate, but the overall duty cycle of the device would be very low. Maybe it does this like once in half an hour, and then then what matters, I suppose, is more like at least some sort of long-term average of the power consumption.
Yeah, one can perhaps view it as an alternative to this uniformly good spectral efficiency that we were talking about, where it's sort of based on that you opportunistically, when you need data, you will always have a good data rate. But if you instead can predict what data you will need, then you can opportunistically download it when you have a good coverage.
Right.
And download huge chunks of data, and then hopefully what you're looking for is already there.
Right. Of course, peak power consumption will remain an issue, right? Even you couldn't, in a handheld device, a battery would not be able to supply a kilowatt of power even over a 10 millisecond window. Even though the, say, average power or the amount of energy consumed in itself would be very small, the battery might not be able to deliver such a high current or such a high peak power. So there are various issues here with what the electronics are actually able to do. But in terms of average power consumption and dissipation of the heat, it's hard to see that applications in handheld devices would ever need to support transmission with these high rates continuously, such that the energy dissipation becomes a problem, or heat dissipation becomes a problem. Yeah.
Okay, let's switch to the third and final topic, NOMA, or non-orthogonal multiple access, which I noticed that a lot of people showed much interest in, and that is also in line with what the research community have been considering in the last 5 to 10 years. There's been a lot of research on this topic. So I have a first question to you. I wonder if NOMA requires synchronization between users. Do all users need to transmit at the same time for the interference cancellation to work? What if their transmissions are like half overlapped?
So I suppose in the question here, NOMA refers to like uplink NOMA, right? So multiple users transmitting simultaneously, and then the base station decoding, which, I think arguably, is that NOMA or not? Well, what is NOMA, what is not NOMA? I think we touched that question in the NOMA podcast we did the other week. But really what this is just multi-user detection, right, on uplink, and which can be implemented through a variety of means. I mean, if you have an antenna array, then you do the usual spatial processing. If you don't have an antenna array, you can do like successive interference cancellation and so forth, or joint maximum likelihood decoding, which, by the way, has been well known for a long time, way before the acronym or the name NOMA came to use. But as alluded to in the questionnaire, it's correct that for any form of multi-user detection to work on uplink, the transmissions have to be synchronized, right? I mean, the symbols have to say overlap. Obviously, yes. So the short answer is yes. There is a requirement on synchronization for multi-user detection on uplink, also more recently known as NOMA or uplink NOMA, to function. Yes.
And in the downlink, if you consider power domain NOMA, is it the same synchronization there?
In the downlink, it is not as critical, right? Because in the downlink, then the transmission from the base station is a superposition of signals which are destined for different terminals. And the idea is that some terminals are able to decode also transmissions intended for others. Now, that decoding in downlink can work irrespective of whether or not the terminals are mutually synchronized. I mean, they have to be synchronized so that they can decode the transmission from the base station, but there's no like requirement that they have to be mutually phase aligned or anything like that.
But if they have different amounts of data to transmit, I guess the easiest thing would be to chop up so that you design a transmission in one way when both of them have to transmit at the same time, and then in another way when the other one have data left and the first one is done.
Yeah, so let's see. So you mean on the uplink now?
Yeah, or in the downlink. I mean, one needs a big file and one needs a small file, and you can deliver one file faster than the other one. Then I would guess you would chop up time so that you are transmitting first to both, and then there is something left for the second guy, and then you are transmitting in a different way.
Yeah, I think that's probably how you would do that in practice. Yeah.
You mentioned in the NOMA podcast that the combination of massive MIMO and NOMA is only desirable in line of sight scenarios. Why only in that scenario?
So massive MIMO and NOMA. I mean, the point here, I think, is that with massive MIMO, if you have a propagation environment that offers enough scattering, or you have line of sight where the users are located at distinct angles that are well enough separated that the terminals fall in like different beams that don't overlap, right? Then there's no added benefit really of using NOMA. You just use spatial processing to separate the users, and that's it, full stop, more or less. But if you have two users that fall in the same beam, so let's say they are, I mean, in the extreme case, located in let's talk about that, say, line of sight, right? So you have two users that are located at the very same angle as seen from the base station, then their channel response vectors will be identical. And then at the base station, if you apply any sort of spatial processing, what you'll see is, well, two scalar channels that just mutually interfere with one another. So the whole system will be equivalent to a single antenna system with single antenna MAC channel with two interfering users. And yes, it's true that power domain NOMA can offer some added rate for such channels, but that this is essentially the only case, right? Because again, once the users are spatially separated, then you apply spatial processing and you get interference-free channels or virtually interference-free channels to them, and then there's no benefit in using NOMA.
Yeah, and I think this is touching upon an important thing when it comes to NOMA, namely that you can create examples that you can simulate and analyze mathematically where you see big gains. For example, the scenario you described, that might not need to have exactly the same channel, but as long as they are close together, they will be roughly the same, so they fall into the same beam. But then if you are considering a base station that is serving a big coverage area, you put up users randomly as in reality, then the probability of that happening is very small. So if it happens 1% of the time, and then you can improve the performance by 20%, then overall, your system will not be that much more efficient.
Yeah, it's a good point. I mean, you can always design channel models or scenarios where you see a gain, but the real question is, how representative are these scenarios for situations that you would encounter in practice, right? Yeah, all right. Great. I think we are close to finishing up for today. We got one more question left, and this question is also on NOMA. And the specific question is that many papers on NOMA optimize the power allocation to maximize the sum rate. What kind of power constraint is needed to enable decoding? Do you want to have a go on that question? Yes.
So if we are considering single antenna scenarios, so there's just scalar channels, then what we then can do is that we can actually order users, saying that one user have a better channel than the other one. It's stronger, so higher SNR. And in that case, it doesn't matter how you are transmitting to the one who have the weakest channel. You can always decode that signal at the one with the better channel because you have a high SNR. So when you are choosing how to allocate your power between the two users, you can allocate your power in whatever way you like. Then depending on how you are allocating the power, you will get different rates for different users. And I think that one way of building such a system in reality would be that you're picking your power in a particular way. Then from that you can compute mathematically, how high is the rate that you can support for the weak user and for the strong user. And then you take that rate, you look at the list of coding and modulation schemes that your system is supporting, and you pick the modulation and coding scheme that is closest to the theoretical prediction, but probably below that number. And then you operate like that. And then there is no particular constraints apart from that you should select the power somehow. But the person who was asking the question also provided a link to a paper where I think a different approach is taken, namely that if you're first selecting what kind of coding and modulation schemes you would like to have for your different users, and then after that you're allocating power, then you will have to think more carefully about your power allocation, because you want to make sure that with those modulation schemes that you already have selected, you have a decent probability of decoding the signals. So in those situations, there's a lot of more complications that are created. I wouldn't build it in that order, though. I think it's better to first allocate the power and then select modulation and coding scheme.
Yeah, or select them jointly. I mean, I think in the end you'd probably want to select, power control and constellations and coding rates and all this jointly somehow. But I think another point here is that, I mean, most of the information theoretic literature makes some sort of assumption, implicit or explicit, of Gaussian signaling, right? I mean, of course you can always work out constellation constraint capacity and so on, but a lot of the papers on these topics seem to start off from a Gaussian signaling assumption, in which case we have a simple expression for capacity, which is a log 1 plus SNR type of formula. And there's at some point here you'd have to, I think, consider, if you use practical coding and modulation with maybe QAM symbols, then, well, to start with, that's not a capacity achieving signaling scheme, right? So to do any sort of meaningful information theoretic analysis, you have to work with a constellation constraint capacity instead, which in many cases, by the way, is close to the capacity of Gaussian signaling. But this issue of constellation points colliding or overlapping or not being separable, that's entirely a consequence of the specific modulation scheme selected. So I would argue that you probably want to choose. It's not even clear, I mean, that you would want to use a uniform QAM constellation or what sort of constellation to use here. So in the end, I'm sure that there are many things that can be optimized, although the gains are likely to be quite minuscule.
Yeah, and this is also putting the finger on one of the issues that NOMA has, that it creates a more complicated way of selecting the coding modulation schemes, because you're coupling those things together with multiple users. And and also briefly mentioning, when you have multiple antennas, the channels are not identical. You might have one user with a better SNR than the other one, but then if you beamform signals towards the different users using different beams, then the effective SNR that you get with certain beam will not be the same as the SNR that you have if you only are measuring your own beam. So then it becomes more complicated to find that, okay, can we order users saying that one have a better channel and the other one so it always can decode? Well, maybe not if we are also putting the beamforming into the picture.
Yeah, so I mean, I think we're opening like a Pandora's box of optimization problems here, right? That might already have been solved. I don't know, because there are so many papers on NOMA and its variations.
So maybe the bottom line is that in the elementary form, there is no particular power constraints that are needed when you are allocating the power. But when you go into more details, there will be plenty of them showing up. And it's important to always reflect on when you are going from a simple model to a more advanced model, what is changing, what additional power constraint do we need to care about.
Yeah. All right.
Okay.
Great. I think we are through. Or did we have any more questions, Emil? I think we covered it all. Huh?
Yeah, I think this is everything that we collected for this episode. And as usual, we love to get your questions and your feedback on the episodes. And I'm also sometimes answering more technical questions on our YouTube channel, but we are gathering questions that are more easy to answer in this format for different podcast episodes. So next time we will be back with another topic, and please continue asking questions and we will return to answering them in later episodes. So thank you, Eric. I always enjoy our discussions. And
thank you, Emil. It's great fun as always. And
bye-bye.
Thank you. Bye-bye.